Hello, and welcome to today's webinar, UAV Design and Applications, Autonomous Relative Navigation and GNSS Robustness for UAV Systems. This is brought to you by our sponsor, Septentrio. I'm Allison Barwatz from North Coast Media, digital editor for GPS World magazine, and I will be your event manager. Before we begin, I'm going to go over some ways that you can participate during today's presentation. Although you are currently in a listen-only mode, we encourage you to ask questions throughout the presentation. Just type in the text box at the bottom left, then click Submit to place your question in the line. You can also submit questions via Twitter by using the hashtag SeptentrioWebinar. Questions that were submitted during registration have already gone to our panelists and may be covered in this webinar. Some questions may also be answered in an upcoming issue of GPS World magazine or in one of our e-newsletters. We strive to answer as many of your questions as possible. If you experience any technical difficulties during today's event, use the same Q&A box at the bottom left to tell us about your issue and click Submit, and assistant producer Kelly Limpert or I will personally assist you. Finally, a recording of this webinar will be available tomorrow afternoon at gpsworld.com/webinars. You can get to that page now and bookmark it by clicking on the header above your slides. A link to the on-demand recording will also be emailed to you when it is available. Now I'd like to turn today's event over to our moderator, GPS World editor, Alan Cameron.
Thank you, Allison, and welcome to everyone around the world. I can see that we do indeed have attendance from around the world on this webinar on different aspects of UAV design and use. I want to thank our sponsor, Septentrio. Septentrio will also be presenting during the webinar. I want to thank all 5 of our speakers, and in a moment I will introduce, or I'll give you an overview of our speakers, but while I'm doing so, you'll see the first of 5 questions that we're going to ask you, our audience, during the webinar, just to get an idea of your interest, your needs, your requirements, and so forth. So there's our first question. Who are you? We'd like to know who you are. 4 choices there. If you'll select one and hit Submit, then your screen will return to the presentation of the webinar. While you're making your votes, I'll tell you that we are hearing from 5 speakers on 4 topics today. First of all, we'll hear from Dennis Akos, professor at the University of Colorado, and his student Joshua Stubbs, talking about GNSS robustness aboard UAVs. This has to do with radio frequency interference within the relatively small confines of the instrument section, sensors and transceivers and so forth aboard a UAV. We'll be hearing from Dr. Jeff Fayman from Geodetics. He'll be talking about an autonomous relative navigation system that Geodetics has developed. Relative navigation capability to fulfill a broad range of unmanned missions, among them aerial refueling. After that, we'll hear from Chris Miser, a former U.S. Air Force officer who has gone into the private sector with his knowledge and expertise on designing UAVs, and he'll talk about practical aspects of GNSS integration aboard a UAV. And he'll be followed by Leyssens from Septentrio with more practical tips for integrating high-accuracy GNSS aboard a UAV. Now, we are going to look briefly at the results from our poll. We've got a few designers. We've got a little over a quarter of you are UAV users. About 10% are both. And the bulk of our audience is neither, but obviously you're interested in UAVs or you wouldn't be here. I'll return with more questions in between our speakers. Right now it's time for our first presentation from Dennis Akos and Joshua Stubbs. They're going to talk about signal robustness aboard UAVs. Dennis and Joshua, the floor is yours.
Thank you, Alan. It's good to be on with such a great group of people. We're going to talk a little bit about some experimentation we did in an academic setting here at the university, working a little bit with our UAS Center Recov here at the university. So just a bit of background. My background is really on the GPS GNSS receiver, and curious what role they're going to play in the integration of UAS, UAVs in the National Aerospace System. You know, the FAA is taking steps there right now, and our center has come to me at different times, said, hey, we had some problems, our GPS is on and off, can you tell me what's going on? So I think it was last summer, Joshua and I got involved and did a simple case study, simple experiment to see really what would happen, mainly looking at radio frequency interference. And of course, everybody wants the ultimate, the RTK, the centimeter level positioning, because of all the abilities and scientific applications that will enable for these type of platforms. But it's important to remember, if you think, and I'm not an expert by any means in the subject, but if you think about what the FAA has done using GPS in aviation, they are not using RTK, mainly because of the robustness issues. So how that all plays out, that is yet to be determined. I'm not working in that sector, but we have done some simple experiments working with some of the RFI, and then looking at some of the simple RTK experiments. I'll talk a little bit about the RFI, and Josh will talk a little about the RTK. You know, so if you look at this package, the picture right here, it really gives a picture of what's working on and what we use for most of our academic work with our UAVs, a small form factor UAV, and there's a very dense set of electronics. And just from some of our past work in working with automobiles and other handsets, when we saw this, we said, oh, what a mess. How is the GPS even working in close proximity to all these electronic sensors? And they said, hey, it works fine, not a problem. But, you know, the concern really was, is it really working fine? Because they weren't really some of the GPS expertise. They were more working with the airframe, some of the vehicles. So is this really a problem? So that's one of the pieces we wanted to look at. And as I mentioned, RTK, real-time kinematic, you know, that's using the carrier phase measurement, which is the least robust of all the GPS GNSS measurements, and a differential mode to get centimeter level type accuracy. Truly amazing technology, will really enable a number of different applications, and to put it on a dynamic platform such as a UAV, UAS, really would be fabulous if you can get the robustness that's going to be needed. So that's really what we were looking for. So we did a relatively simple experiment. We looked at the GPS measurements on this UAS in the presence of RFI. And we didn't inject any RFI. We basically said, what are these auxiliary components, or not so much auxiliary, but the components necessary for flight? And this is a very minimal scientific payload. We don't have many sensors on here, but what do just these components needed for flight really have as an impact on the system? Taking that system and looking at a spectrum analyzer, powering things on and off, really look at the frequency spectrum around the GPS band. So we conducted 3 different experiments. We took the antenna outside the airframe just to see if that had an impact, put the antenna inside the airframe, which is their usual configuration, and then the antenna inside the airframe with all the systems on, and looked at the difference. So this is a picture of the frequency spectrum you'll see from the GPS band. If you're not familiar with it, the GPS band, the sync function you see from the L1CA code signal is right there in the middle. Typically, for a single satellite, that signal power is buried below the thermal noise floor. You can't see anything whatsoever. But because all the GPS satellites are running a little bit hotter than their spec, and you're seeing the cumulative power of all the energy of all the GPS satellites in view, you see what we refer to as a GPS bump. And that's just the peak of that sync function popping right above the noise floor. And this is a relatively clean environment on our engineering building. We don't see many tones, anything else. And this is what it would look like, you know, when everything was off. If I compare that with the next slide here, when we turn on just a basic auto flight systems, basically the GPS bump is masked. It's been hidden by all the interference, and we have a considerable increase in the noise floor. Again, you know, this configuration works fine. It does get a GPS solution. They just said, well, it doesn't quite work as well as we would like. What's going on? So this was the first insight we had. Hey, you know, those systems and where that antenna is placed, that looks to be problematic. And, you know, one of their fundamental metrics were, okay, how many satellites am I tracking? And during the course of this test, we looked at that same metric, whether it was inside, outside, or the system was off, over a short period of time, just so we had the same satellite constellation in view. They said, hey, look, we get 12 satellites. Everything's working great. You have to remember, the GPS receiver has evolved to a state now where it has incredible sensitivity. So even when it has a fairly low CDAN-NOT signal-to-noise ratio, the receiver can hang on and track those signals. So if you go to one level deeper to the metric of CDAN-NOT, basically you see a fairly considerable dip when the systems are turned on. So yes, of course, we don't lose any satellites, but we see a 7 to 10 dB drop, and this is average across all satellites, when the other instrumentation is turned on. So yes, you can get a GPS position, but even more problematic is going to be if you try to do an RTK type solution in terms of cycle slips and how well you're going to be tracking that carrier phase. So merely trying to make that piece available and informed to the UAV community to understand that, hey, you have to be aware if you're putting this antenna in close proximity to other sensors, how is your receiver going to respond to that? And if you have a position solution, that does not mean you're not being impacted by the other sensors. So just a table here kind of showing what happens if we did max CDAN-NOT, min CDAN-NOT, and basically with the systems on and off. And the bottom line, again, for this one single case study, basically in a system that the UAV community, the UAV folks, thought, hey, it's working well, not a problem, you did see a fairly significant 8 dB penalty on average for all the satellites that were in view. And what I'd like to do is turn it over to Josh now to talk about some of our RTK experiments we did with eventual goal of trying to couple these two pieces together.
All right,
Josh?
Thank you for that, Dennis, and thank you everyone else. Very interesting. So yeah, I'm going to talk about the case study we did for the UAS RTK measurement, and what you see here is a block diagram of our setup that we used. And for this initial experiment, there were three main things we wanted to sort out in order to continue this work. First of all, we needed a platform to test our RTK setup on. And for this, we selected a car, as this introduces dynamics into the system, but it's also relatively easy to use. And it's simpler to do many tests compared to using a large UAS that would be required for this kind of a setup. We needed a truth reference system too, so in essence something to compare our receivers against. We needed to make sure that we had an accurate truth reference system. In a static case, this is quite simple at least, because you know the coordinates of your antenna and you can compare against these coordinates. But in a dynamic environment, this will obviously change a lot. So for this, we used a high-end triple frequency GNSS receiver coupled with an IMU, an inertial measurement unit, in order to get measurements during conditions where GPS and GNSS might not be available. The truth reference data was post-processed using precise orbits and PPP to get as accurate of a position solution as possible. And for these tests, we assume this to be completely true. The receivers we wanted to test, for simplicity, we logged the data on board the car, and then post-processed the results, emulating real-time using software called RTK-lib. And this is just as it was easier to do this than to use an RTK setup where you need mobile data communication to the car from a base station too. But it's emulated to be real-time once it was processed. So going on to the test itself here, this is a picture of the car we used. You can see here the GNSS antenna on top and the IMU bolted securely to the car. Now, I want to mention that using a car might not be ideal. There will be different dynamics involved with the car compared to UAS. So UAS will involve some heavy rolling and pitching, whereas a car obviously won't be doing any kind of maneuvers like that. However, with the car, we can stress the GNSS receivers by driving into environments where you can expect multipath and sky blockage, which will at least introduce some dynamics into these measurements that we're interested in. So for the test, we drove around the University of Colorado in Boulder and Boulder itself. And you can see the path here in this slide. And the drive included parts with the open areas, so with great sky conditions. It included areas with partial sky blockage, trees, buildings, and we also drove through a parking garage where the sky was completely blocked. So you should expect very poor performance from the GNSS receivers. However, the truth reference system will work using the IMU that I showed earlier. And to keep this brief, I have here the tabulated results from this test that we did. So first of all, I'd like to mention that if you see here the GPS L1 receiver that we've labeled A here did very poorly compared to the others. And we've seen this several times using this receiver in other environments too. So I'd like to say don't pay too much attention to this, as this receiver seems to have some issues that need working out, not just for RTK, but for standalone positioning too. All of these receivers are receivers you might find on a UAS, so that's why they were selected. And the post-processing was set up to use a fallback mode of standalone GPS or traditional GPS, as this is what you'd expect to use on a UAS, since it is better to have some kind of position solution instead of no position solution. So the 2D RMS and 3D RMS here is the results of all the data points, including ones that were not in RTK. So this is for the entire drive, which lasted around 50 minutes. And if you compare receiver B to receiver C, you see receiver C has a lot higher accuracy, although it is a triple frequency receiver, so this is kind of expected. Interesting to note, I think, is the availability is roughly the same, actually slightly better for the single frequency receiver. And availability here, I should say, is defined as how many data points could a position solution be calculated out of compared to how many data points we would have had if the conditions were ideal. And out of these available data points, we get the next row here, which is the RTK solution. So how often could RTK be calculated out of our available data? And it's roughly the same for both receivers. It's 100% or just below 100%. And the real difference we see here between the receivers is when it comes to how often fixed solution could be calculated compared to a float solution. And a fixed solution is the highest accuracy mode of an RTK system. And float solution is more accurate than a standalone receiver, but it's not as accurate as a fixed solution. So we see here where the triple frequency really comes into play as the ambiguity resolution improves for the triple frequency system. So this was our initial results for this, which we wanted to use to couple this with the RFI that Dennis was talking about earlier. However, unfortunately, we ran out of time. So to conclude what we've talked about here, in our case study with the RFI, we've shown that RFI can be problematic for US platforms and users. There was a high impact on their carrier-to-noise ratio that was coupled with the dense electronics on board. However, since the number of satellites didn't change between the tests, this might be an issue to a UAS operator that is monitoring the number of received satellite as a quality measurement, as if this is your quality measurement, you wouldn't notice any difference between the tests. However, we did see, like I said, the large impact on the carrier-to-noise ratio. And this will become important to RTK users too. As Dennis mentioned, RTK is quite frail, so this RFI needs to be mitigated for RTK use. And from the RTK experiments here, we saw that RTK remains a useful technique to use on scientific payloads. It's been done before, and it is used. And like Dennis said, it is unlikely to be used for UAS navigation, as it's likely that UAS will follow manned aviation and use certified receivers and RAM and so on. And like I said, minimization of this RFI that we saw in the first experiment will be critical for robust RTK performance. And that's all for us, so thank you very much for listening, and back to you, Alan.
Thanks very much, Josh, and thank you, Dennis. We turn now back to you, the audience. A question. I can see from the questions coming in from the audience there's quite a bit of interest in different sectors for a UAV application. So we'd like you to let us know which markets you are currently involved in. You'll see a selection of 5 there, and then the all-inclusive, or not all-inclusive, but other inclusive other category. If you'd take a minute now to give us, to identify yourself by sector, we'll return to those results after the next presentation by Jeff Fayman from Geodetics. And I should have said at the head of the program, the top of the program, that both of our first 2 presentations, the one you just heard from Dennis Akos and Joshua Stubbs, and this one from Jeff Fayman from Geodetics. They are full-length technical articles in the April issue of GPS World magazine. So if it went by you a little fast, or if you'd like time to mull over all the details and get more context, turn to the April issue. Now over to Jeff. Take it away.
Thanks, Alan. My name is Jeff Fayman. I'm with Geodetics. And I'm going to be talking about work that we've done here on aerial refueling applications and how we went about doing that, and the type of applications that the technology enables. So autonomous aerial refueling under GPS-denied conditions. Just to mention a little bit about the GPS-denied part of it, a lot of our customers ask us in the applications that they're involved in, what happens if you lose access to GPS? We heard a great presentation just before this one about RTK and kinematic processing on UAVs, and the next thing is, what do you do if you don't have GPS at all? Not even for an autonomous solution. So we'll address that a little bit here in this presentation in the context of relative navigation and for the application of aerial refueling. Autonomous aerial refueling, we all know that UAVs are becoming more and more used out there, and both in civilian applications, agriculture and the like, as well as the military. And in the future, more autonomy will require new technologies, but the benefits that the autonomy will bring and the technology will bring will be increased flight safety for manned operations, so sort of as a backup to the pilot, to indicate that the pilot might need to change course of action based on what the sensors are seeing. And for aerial refueling, it would be optimizing the refueling operations. So if you can bring in planes quicker, you can save fuel in that respect. And the goal, of course, is to be able to completely automate the process of refueling these UAVs so that they can come up behind a tanker without any input from a pilot and operate the refueling operation. So refueling automation relies on access to what we call relative navigation or precise relative navigation between the aerial refueling tanker, which you see here, and the platform that's receiving, or the receiver of the fuel. And when we say relative navigation information, you can see the table here underneath the picture. We call that relative TSP, so it's relative position, relative velocity, and relative attitude. Those are all things that we're familiar with in the absolute sense, yaw, pitch, and roll of an aircraft, or position in an Earth-centered, Earth-fixed coordinate system. But this is a little different in that it's relative, so you need to know what the information is between the aerial refueling tanker and the receiver in a relative sense. We call that relative TSP, or relative navigation. And so we've developed a system we call the GeoRelNav, which you see here on the left. It consists of a pair of inertial navigation systems that are distributed, one on the tanker for aerial refueling and one on the receiver of the fuel. And there's a data link in between them. Data flows from what we call the secondary, and it flows to the primary, and the relative information, this relative TSP that I mentioned on the previous slide, is computed and used for whatever application is it's needed for. So another application, in addition to aerial refueling for this, would be a shipboard landing of a UAV. You have the ship being affected by dynamics of the sea. You have the UAV being affected by dynamics of the air, and the UAV needs to compensate for any kind of motion that the landing point on the ship is undergoing due to the waves that it's going through. So that requires very accurate relative TSP, or relative information, in addition to the aerial refueling application. So these are some of the applications that our system is being used for. Maintaining safety of flight by ensuring that the receiver, the guy getting the fuel, does not exceed a certain velocity on its approach to the tanker. Making sure that it's moving with a sufficient velocity to the tanker so that it's not just loitering there behind the tanker. It needs to actually approach and connect. And it provides data to the guys in the aircraft and are designing the different instrumentation on these aircraft. It gives them information to help them refine their control laws. And you can see there a picture of an aerial refueling tanker and some of the aircraft that this system is operating on. And the goal at the end is to provide a fully autonomous aerial refueling capability. So we break up the problem into relative navigation phases, which you see here. So the approach phase is when the UAV, or it could be a manned platform as well, approaches the tanker. In this phase, the data link is open, so there's no communications going on. They're both navigating on their standard navigation systems. And then when the data link closes and they're within range to start communicating, we transition to the engagement phase. And in this phase, we initialize the relative Kalman filter, which is a class of Kalman filters for doing this type of work, relative navigation. And the relative Kalman filter is operating during the entire refueling operation to make sure that the platforms are maintaining their relative state. And then when the refueling operation is done, the departure phase, the secondary platform or the UAV departs the area, and other UAVs can come in. So that gives us sort of a basic construct on how to look at the refueling application: approach, engagement, and departure. So there's data, as I mentioned, being transmitted from the secondary platform to the primary, and there's no requirement on how the secondary and the primary are defined in terms of the aircraft. The primary could be the tanker, or the primary could be the receiver. It just depends on what the application is. But data flows from the secondary to the primary, and what flows is the position information computed on a moving baseline RTK. So there's a pair of GPS receivers with carrier phase observations. We offload the observations onto the processor, and we do what we call an epoch by epoch process and compute the precise relative position on the moving baseline. And that technology resides within the processor on the RelNav system. In addition to that, we have the raw GPS observations transmitted through the data link and the raw IMU measurements. Remember, this is a relative navigation state, so those raw observations, just like they would be used in a standard observation navigation system, are used also in the relative navigation solution. So you're doing a relative navigation solution with a relative Kalman filter using these same observations, but in this case from two platforms that are moving relative to each other. So data transmits through the data link, and the relative solution is computed. So the question arises, and this is a question that we're asked quite often, if you're in a GPS denied environment, maybe you're being jammed, maybe you're being spoofed, maybe the airframe is being masked. What do you do if you don't have access to GPS, if you can't use this relative high precision real-time moving baseline real-time kinematic solution? So the question is, how do you solve the problem without access to GPS? And the answer is, from our perspective, is sensor fusion. And this is a sensor fusion architecture that we designed to and implement. And the relative navigation system here, the RelNav, is an instantiation of this architecture. And there's a lot of different sensors on the bottom of this thing, but the bottom line is that the data flows through the architecture from the bottom to the top, from physical hardware to the navigation solution. The idea is if you lose one of the sensors in this architecture, you have other sensors available to you to compensate the loss of the sensor. So if we lose GPS, we have other sensors that are allowing us to fill in for the lack of GPS. And a couple of the sensors that we use here: stereo vision, stereo pairs, cameras, and LiDAR. These are laser scanners that give very dense point maps. And it turns out that using information from these sensors, we're able to extract equivalent information to what we would get from a real-time kinematic solution, but these are completely independent of GPS. So you can see examples. We use a LiDAR here, a small LiDAR, a stereo camera, and there are some of the characteristics of these sensors. And you can see the drogue and the system, the aerial refueling system down below, and how we model what these sensors are supposed to be identifying on the bottom right. So we've done quite a bit of experimenting here using the various other sensors to replace the GPS. Again, these are all being fed into the relative navigation solution. It's just alternate sensors that are not dependent on GPS. And it turns out that we can basically replace the GPS there with an accuracy of plus or minus 10 centimeters using these variety of sensor replacements for the GPS. And the idea is, in the sensor fusion, is that all of these things are operating simultaneously, and the system is looking at each of the solution, voting, and making sure that the output of the system is as good as possible given the information that's available at each time instance through the operation. So the impact of visionating, we're able to do things that we can't really do with the GPS system as well, since we're directly measuring the relative position to the moving drogue, the thing that's outputting the fuel. We can actually compute the relative position to that point, something that would be more difficult to do with a GPS-only solution. Another thing that this allows us to do, of course, is if you drop GPS completely, if you're jammed, or as we heard in the previous presentation, if your designers didn't do a good job of taking care of the RF interference, you might not have as good a GPS as you need. Well, here you've got some alternatives that give you the ability to overcome those problems. As Alan mentioned, this work that we've done, it's a very brief overview that I just gave you, but there's a little bit more detail in this latest issue of GPS World, and you can see here a screenshot that we captured from the GPS World website. I invite you to go there and take a look at more details if this is interesting to you. And more information about what we do here can be found on the Geodetics website, geodetics.com, and I'd be happy to answer any questions that come up or talk to you, and that'll be it. And I'll turn it back over to Alan. Thank you very much.
Thanks very much, Jeff. Time now to see who you are in the audience in another perspective. We asked you which markets you're currently involved in. About a fifth of you are in agriculture, 10% in construction, small small portions in mining and inspections, almost half in mapping and surveying, and a little bit more than half selected other for their sector. Let's take another question for you. Whether you're a designer or a user or another, which sensor do you use, or which sensors are you most interested in using? If you'll select an answer from that question, and while you're doing so, I will introduce Chris Miser. Chris Miser is a former U.S. Air Force officer and engineer who did a lot of work on UAS while in the service, and since coming out, he's founded his own company, Falcon Unmanned, based in Colorado. They're involved in a number of very exciting applications, but I will let Chris tell you about them. Chris, go ahead.
Thank you, Alan. My name is, as Alan said, my name is Chris Miser. I'm the owner of Falcon Unmanned. Let's go ahead and click my slide forward. I'll be talking to you today about the practical considerations for integrating an RTK solution into a professional UAV. As Falcon Unmanned, we make two aircraft right now. We have Falcon, which is a fixed-wing aircraft, and Falcon Hover, which is our multi-copter. The thing we're known for is having the only interoperable modular family of UAVs, and the fact that these two platforms share payloads, as well as batteries, as well as ground control stations. So when we were getting into the RTK game, we wanted a modular RTK solution also that would work with our existing infrastructure. We understand that anyone that's in this market is going to be looking for a multi-mission UAV, meaning that it can do lots of different things. There are a lot of platform-specific UAVs out there that are just interested in mapping. Some are just interested in RTK mapping. We're on the other side of the fence where we look at UAVs as a payload truck. You need a really good truck that can do all the missions, and RTK GPS capabilities are applicable to some of those missions. So we only want to have it on the plane for those applicable missions. As it pertains to what's in our system that's related to RTK, we have the Pixhawk autopilot. We use the autopilot code base. We also have a communication structure that does allow us a auxiliary serial port. So from practical considerations, you have to be able to get data from the ground control station up to the UAV, either bypass the autopilot or through the autopilot. In our particular solution, we're using autopilot with Pixhawk. They have recently integrated RTK capability into the autopilot, so we are passing information through the autopilot. And we do that through a combination of both autopilot, which is the firmware on the aircraft, as well as Mission Planner, which is the control software on the ground control station. Moving to my next slide. We are partnered with Septentrio with their solution, and I can speak to it firsthand because of their modular type design. I've integrated a lot of different sensor technologies, and this is not a sales pitch from me. I wasn't paid to say this at all. I find this module to be just there's very few things on the market that are easy to integrate, and this was about as easy to integrate as possible. It's low power. It's a nice size and volume. You'll see it in the next slide. The antenna is a dual frequency antenna. Solution, or the RTK unit is a dual frequency, which you'll understand a little bit later is important. I'm going to talk a little bit about camera selection, how we collect that data, and the biggest thing that we had to look at was what is interfering with this unit. Because no matter how well the units are made, our aircraft are emitting a lot of different types of energy, and that interferes with these types of things. Looking at the actual RTK unit, you have a number of serial ports. You have an SD card for doing the onboard data logging. You have your power input, and you have a hot shoe input. In our particular solution, that little box is what is holding the RTK unit, and that's an iPhone 6s for reference. So you can see the size of the entire unit next to my phone. And this unit is a modular unit that we are putting on top of a camera payload when a customer would want it. As you can see, I have a connector for the hot shoe on the front of the RTK unit, and on the back side, you can't see it, but there's wiring for the serial communications as well as power. And then we have two little side ports to access the SD card as well as the USB port. So how do you sync the camera? The way we sync these things is using the hot shoe. There's nothing that is nearly as accurate on these camera systems as the hot shoe. So for example, we did look at the A5100, Sony A5100, which is a popular mapping camera. And if you use their side input trigger delay or trigger, the delays varied wildly from 5 to 50 milliseconds. So it was, and when we're traveling at 14 meters per second, that leads to up to 70 centimeters of error, which is completely unacceptable for RTK or survey grade GPS. So the solution is to use the hot shoe, and there are a number of cameras that have that hot shoe, which ties to your next question of which cameras do you select. We have integrated the Nex 7, the A6000, and the Ricoh GR and the GR2. A couple of other cameras that are on the market that have hot shoes that could be used are the A6300 and the Sony A7R. This is not by any means a complete list. These are popular UAV mapping cameras that are out there that do have hot shoes. And as you see in my payload there, that's a payload that will support either the A6000 or the Nex 7. In that particular payload for that individual photo, we have the Nex 7, and you can see the RTK module on top. So from a practical consideration, how do you collect the data and get it to fused with the data at the end? Because really, as I mentioned before, the UAV is just a truck. The process is what's important of how do you collect the data. So in an RTK solution, you have a base station that's feeding into the mission planning ground control station software that is transmitted up to the plane over the wireless communications network into the autopilot. That goes out to our RTK unit, which gets the corrections all the way back from the RTK network or the base station, and that data is logged in the autopilot data flash. The other option that you have is post-processing the data, where you take the SD card off of the plane at the end and take the SD card from the base station, and then you post-process them. In the end, you're going to get the same results, I believe. So let's talk about the biggest consideration that we had to work through, which was interference. The GNSS signals are pretty weak. All GPS signals are weak. You got satellites up in geosynchronous orbit, and it takes a lot of power to get them out there, but when they get to the ground, it's pretty weak signal. So, and UAVs do have a lot of noise. We saw a picture at the beginning of this call which showed some congested avionics. I'll tell you that when you look at our avionics board, it's a lot more congested than that. And we have a lot of different things on there generating a lot of different sources of noise. Ironically, in the end, the largest source of noise for us was actually the Next 7 in this particular case. The GoPro data is from a different data set, but in my practical usage, the Next 7 was actually the largest source of noise. So bottom line, we copper shielded the inside of the little RTK box, and that helps substantially. So that leads to how do you prevent this, and by far the best way is to do some ground and bench testing to determine what your sources of noise are by turning on the unit and taking a look around and looking in the software that you have to see the satellite signal strength and seeing how and where your sources are. Turn items on incrementally. You can always increase the distance. Sometimes that's not an option in small UAVs, in which case you have to turn towards proper routing of the cables as well as shielding. And in our particular case, we were able to use some copper tape or copper thin copper shield to be able to mitigate the interference that we were seeing. So with that, I'll hand it back to Alan.
Thank you, Chris. We'll look at, as kind of in line with what you were saying, we see the responses from our last question. 3/4 of our audience is using visual cameras, about 1/3 using infrared cameras, 1/3 using LiDAR, excuse me, 1/5 hyperspectral cameras, and almost half using other sensors as well. Let's take a look at our next question. What height accuracy do you require? Are you on the order of centimeter, decimeter, half a meter, or is height accuracy not so important for you in positioning? While you're answering that question, I will introduce you to Jan Leyssens from Septentrio. Jan has quite a good feel for the market since he's out there representing the Septentrio product that Chris just told you about. And Jan's going to talk about practical considerations for integrating GNSS aboard your UAV. Jan, take it away.
Okay, thank you, Alan. Hello, everybody. My name is Jan Leyssens. As Alan said, I'm product manager at Septentrio, and one of the areas I'm responsible for is the products that go onto the UAV platform. Chris already nicely introduced let's say, two practical problems people often encounter when they start using GPS on drones. That is the interference caused by, let's say, by other electronics like cameras and other parts, and the camera synchronization. I'll mention a few other considerations that you need to take into account when you want to integrate centimeter level accuracy on drones. The first thing is to realize that there are two main applications for centimeter level accuracy on UAVs, and both of them have an impact on the rest of the choice of the rest of the technology. The first kind of applications, you would say, that's georeferencing. That's tagging or geotagging centimeter level with centimeter level accuracy images or other sensor data, LiDAR data, hyperspectral data. That's something that can be done offline. It doesn't have to be done in real time, but it requires a accurate synchronization of the GPS with the camera, and also it's something that's very handy to have integrated in the image processing chain. The second application, which require centimeter level accuracy in real time, are navigation applications, for example, to have a multi-copter or a helicopter hover at a certain point in space to point the camera reliably to take off or land automatically. And there, of course, the reliability of the position is very important. It's like anti-jamming functionality, anti-spoofing is important. Multi-constellation, reliable error reporting is important, so that if the GPS has a problem, that it actually reports that to the autopilot. To have real-time centimeter accuracy using RTK, you need a data link between a base receiver and UAV. So typically you need these corrections. Where do you can get these corrections from? You can get them either from a local base station that is connected to, like in Chris Mises' situation, to the Pixar mission planner software, and then it's uplinked via the telemetry link. Or you can also get corrections from an RTK network via mobile data. That technology is called NTRIP, and that's easy if you're in an area where this infrastructure is available. Or to get the corrections to the UAV is either via the telemetry link or by implementing a dedicated data link. So it can be using a UHF radio or integrated cell modem on the UAV, but of course that adds more power and weight again. So the telemetry link solution that Pixhawk implemented is quite an elegant solution. On the next slide, I've added a few links to movies on YouTube of what can be done with this concept. You can have a look at them after the webinar. One that shows what can be done using the Asterix MUES together with the Pixhawk integration for stabilized hover to keep the drone steady at a certain location. The second one is automatic takeoff and landing. And while watching the movie, have a look at the environment around. It's not an easy environment for GPS. The third movie is a more professional one. That's from a company called Flying Cam in Belgium. They use a dual antenna GPS receiver to stabilize their flying camera, and they've won already several Oscars with that technology. It's a nice movie to watch. For the other application, for georeferencing, when you don't need centimeter accurate positions in real time, a solution using our approach is what's called reprocessed kinematic is interesting because you don't need the telecommunication link in real time. The software that we made for that is called the Geodetics, and it's a very simple concept. You put the receiver on the UAV, you fly, you take your pictures, and then afterwards you load all that data, the raw GPS data, your base station data, and the pictures into the software. The software will reprocess the accurate positions, look for which pictures these positions apply, update the metadata in the image, and then those images can be used directly in software like Pix4D or Agisoft to create the 3D models. On this slide there, so we did a few tests together with the people from Smart Planes in Sweden. And there we saw that both when using Pix4D and Agisoft software, we managed to get an accuracy of about 2 to 3 centimeters in the resulting ortho model without having to use ground control points, without using ground control points or real-time RTK corrections. One of the questions that came through was, does it matter to have more constellation than one? Yes, it does. This plot shows a picture of a GPS receiver in a forest in Australia, where also that compares when using GPS or GLONASS only, or using GPS, GLONASS, and the Chinese Baidu system. So you see in very difficult environments, having more constellations helps a lot in getting a good RTK solution. Probably not that important for mapping drones that fly high above the terrain, but for people using drones for inspections, flying close to walls or wind turbines or any obstacle, having multi-constellation really adds value. Another question we often get is what's the difference between single frequency or multi-frequency RTK receiver? To understand the difference, I have to, let's say, make it a bit more complicated and say, so the basic idea behind RTK is that the receiver is going to estimate how many phase cycles there are between the receiver and the GPS satellite, which is called ambiguity resolution. If you use single frequency GPS, so L1 only, there's a possible solution every 19 centimeters. If you combine measurements from multiple frequencies, L1, L2, there's only a possible solution every 83 centimeters. So that means that if you use multi-frequency RTK, the receiver has much less possible solutions, so it's faster to find the right one. So multi-frequency RTK initializes typically very fast in a few seconds. Because there are less possibilities, also choosing the wrong one when operating next to obstacles or during high ionosphere activity is very low. So the main thing to remember between single frequency and multi-frequency RTK systems is that multi-frequency initializes faster and is much more robust when it gets more difficult. So these were my recommendations. I think I hand the floor back to Alan.
All right, thank you very much, Jan. I'll have a question for you, Jan, in just a second. Meanwhile, we're going to take a look at the results from the height accuracy that people require, and over half want centimeter accuracy, about 10% decimeter, about the same amount, 10% half meter, and for about a fifth of our respondents, height accuracy is not so important. We'll take a look at the last question, which is which horizontal accuracy do you require? And while people are answering that, Jan, there was a question came in during your presentation. Somebody wants to know a little bit more about geotags, or, well, the key question, is geotags freely available?
Let's say it's not. Let's say it's available. We don't provide it for free, but it's not that expensive. Let's say that.
Okay, thanks very much. Now we are open. The floor is open for questions from the panel, and I'm going to ask the first one that came in. And probably Jan or Chris or both of you will have answers for this or perspectives. Someone wants to know, how big is the market opportunity for small companies to develop special applications for UAVs? If it is significant, which markets or application areas appear to offer the greatest opportunity and traction? What do you say, gentlemen?
This is Chris Miser with Falcon Unmanned. I can speak to just generally speaking about the UAV market. I think there's a huge opportunity in the UAV market, period. The thing that typically delineates the people that are successful versus those that are not successful is actually delivering an affordable and effective product. And that doesn't matter. That doesn't matter whether or not it's hardware, software, or services. There's a lot of people talking about drone applications, but very few people are actually doing it. Everyone's talking. I think one thing that we do is that we actually go out there and do. We don't say we can do something unless we've done it, and I think that's key to this industry. We see a lot of hype and a lot of noise in this industry, a lot of novelties, and I've been doing this full-time since 2003 when I was in the Air Force designing these for the Air Force. And it's always been a constant thing of novelty after novelty. But in the end, the question is, does it actually work? And the novelty wears off pretty quickly when it doesn't work. So that's bottom line. If you do something well, it can be very successful in this industry.
Jan, do you have anything to answer or to add to that as you're out there presenting the Septentrio solution to various clients and prospects? What's your sense of the marketplace, and where is it developing?
Yeah. Well, I think I agree with Chris. There's a lot of applications possible. There's a lot of demand. I think one example is the mapping. I think that's one of the applications where the technology gets mature enough to start doing business. But the advice I would have for, let's say, for smaller companies is say focus on the application, go talk to the customer. Don't just buy parts from the internet and try to build another drone. Really go talk to your customer, focus on application, focus on the payload integration, and actually help them do something. I know it's fun to build a drone, but actually it's you have to do something with it. That would be my advice. Focus on the customer and an application.
All right. Very good, very practical advice, and that aligns with what I've seen in the marketplace or at such marketplaces as Intergeo in Germany. A lot of people are having a lot of fun building drones, but the key business question is what is it good for, what is it, what application is it specialized for, and how well does it work in that application. A number of very creative and ingenious engineers can build an unmanned autonomous air vehicle, but the question is, well, what use do you put it, and how do you make it meet that use? I'm going to look at the answers to our questions, to our final question, that is, which horizontal accuracy do you require? 3/4 of our audience requires centimeter accuracy, a little under 10% a decimeter. Nobody voted for half a meter. That is just not good enough. And less, although nearly fifth said that less than a meter would be good enough. The floor is still open for your questions. I have another one that came in during your presentation, Jan. Somebody wanted to know about EMP shielding, and was that being applied? I see you've answered it online privately, but can you let the rest of the audience know about that?
Yeah, sure. I assume with the EMP you mean the shielding, let's say for electromagnetic interference. What we see is that the receiver itself is shielded, but we see that in most cases interference is picked up by the GPS antenna, which is also mounted very close to the GPS antenna. So to avoid problems with interference, the most important thing is to make sure the GPS antenna is shielded from the rest of the electronics. It's either putting it far enough away or putting some copper tape around the rest of the electronics. So that's my recommendation.
Right, and we saw the importance of that in our first presentation from Dennis and Joshua. Second question, or the second question from our previously registered ones. Jan, you alluded to it briefly when you mentioned Beidou in your presentation. Somebody wants to know, do you have multi-constellation support, and what are the effects due to the multiple GNSS systems now available in the UAV sector?
Oh, I think we see the multi-constellation as really as the future. I think it really helps us providing a more reliable and more reliable solution, especially if it becomes more difficult. Especially, for example, you're going to look at inspections, people operating next to obstacles, or takeoff and landing. Let's say if you want to take off with a multicopter, it's often next to a building or often next to a tree, and those extra satellites from Beidou or the European Galileo can actually help to give you a position or not. So that's the main thing: more reliability in difficult environments, and we see that all over the place.
Yeah, similar to applications in other spheres. Final question, and this comes from our panel. Jeff Fayman wants to know, and I believe this question is directed to Chris Miser. Jeff wants to know, is image time tagging provided by the autopilot or by the camera with the hot shoe? Chris?
So under our system, like I mentioned, there's two processes that you could do. One's the post process, but it sounds like his question is more applicable to doing it RTK real time. So doing it real time, the base station or RTK corrections are transmitted over the wireless communications link through the autopilot into the Asterisk board. The Asterisk board then get the final RTK solution, which is combined with its own GPS data, and that is transmitted to the autopilot. The autopilot senses the hot shoe and does a time tag based on those pieces of information.
Thank you, Chris. Well, we've come to the conclusion of our hour. I want to thank all of our speakers, our 5 speakers, Dennis Akos and Joshua Stubbs from the University of Colorado, Jeff Fayman from Geodetics, Chris Miser from Falcon Unmanned, and Jan Leyssens from Septentrio. I want to also thank Jan and his colleagues at Septentrio for sponsoring this webinar, making it possible in the first place. I want to thank our audience for attending, and please join us again next month. The third Thursday of each month is our date for Market Insights webinars, and in June, that will be June 16th, and we will turn from unmanned autonomous in the air to autonomous on the ground. We're going to have a webinar on the connected car. We'll have Chaminda Basnayaki from Renesas and a panel of other folks. A number of them are invited. I see names here from Sony and Denso. We'll have more information on the website, in our email newsletters, and in the magazine. Please stay tuned. But mark the date, June 16th, for a webinar on the connected car. Thanks once again to our speakers. Thanks to Septentrio for sponsoring. Thanks to you, our audience. Have a great day. And thanks to Allison. Back to you, our engineer.
Thank you for attending today's webinar. If you have any more questions, do not hesitate to contact our presenters at the emails on your screen now. Links to their email addresses are in the bios at the left. An on-demand recording of today's webinar will be emailed to you tomorrow afternoon and will be available online for a full year at gpsworld.com/webinars. If you'd like to share this webinar with your colleagues, you can do so via any of the links on the left-hand side of your screen. You can also download today's slides via the resources box on the left-hand side of your console. Again, you can register for upcoming events or view previous ones now at gpsworld.com/webinars. We look forward to seeing you at a future webinar.